Looks like we're almost there. Welcome back, folks. We're starting off with a good Monday. Remember to unmute myself before class started. And it's official. Welcome back, everyone. I hope you all had a great weekend after getting through our first exam. By the way, for our first exam, I have a notice here, and I sent an email when I returned your graded exam. I had one student with a valid medical reason to extend the exam. And so because of that, I have to wait before posting the solutions as well as the summary statistics. I should have that posted in the end of the week here as well. Also, once all those are posted, if you have questions on your exam you'd like to address to the class, I'd be happy to take them. For the moment, with the exam not completed, I can't answer too many exam questions, but you're always welcome to send me a direct email discussing any question you might have on there. By the way, on the real exam, you have 2 grades that are being given. One grade was just your grade as a fraction of correct points on the exam, and that's what you're going to see as a percentage under grades here. Your second grade was through the syllabus. It was called the course grade, and I was just using this table right here to give you a rough estimate of where you're standing in the class right now. So your homework was weighted as 20%. That's just the web assigned sections that had been due. 15% for the quizzes, just the ones we had. And because we had just one exam, it was weighted as 65%. So that's how I calculated your course grade. Any other questions at the moment, folks, about the exam? Okay, well, this is pretty much how all the weeks in Moodle are going to be going. From week 1 to week 4 here, we had our exam, and then as we go forward, it's as if we're starting all over again, just we're in section 2.5. And as we get closer and closer to around this week right here, the end of this week, I'll be posting the information for exam 2, study guides, and that kind of stuff. And so that's pretty much just the process of our week-by-week schedule here. Elias said, just joined, will we get the feedback on the exam? Yes, you should have had your exam emailed directly back to you using your ISU email address. So if you can't find your exam, just send me a quick email and I'll check out what happened and just resend that exam. Other questions at the moment? Okay. And also, by the way, if we're looking a little bit closely at the schedule going forward this way, we have a midterm week here, but for our class, midterm week isn't anything too super special. I don't have a big midterm exam. The next exam is just exam 2. All that happens on midterm week is at the very end of that week, I just report your grade standing at that time, October, what would that be? Let's see here. I'd be reporting your standing in your class on October 11th for this week here. And so that's all midterms is, just giving you a chance to see where you're at halfway through the semester. So no special exam or quiz or any assignment like that is required. Let me get that back. There we go. So with where we're at so far, we're in a pretty great section in Chapter 2. Chapter 2 is a beast in any calculus class. This 3 credit one or the 4 credit one, that's because it's all about getting used to the limits, and there's a lot to absorb. So we have one last section on continuity. It's just more topics about limits. And then after that, we're going to be using all of Chapter 2 to finally say, what do we mean by a derivative? We haven't even hinted at that, except we've been saying all along, Chapter 2 is just to build the machinery needed to get into the work in Chapter 3. So we're getting really close to that, but despite our excitement, I'll still want to take extra time going through this section as needed. We're a little bit behind on our day-by-day set syllabus, but these are technical topics. So if there's extra class questions in class, I'm always willing to spend extra time there. Well, that's my whole spiel for the announcements today, folks. Any other questions or comments to start us out today? Okay, well, let's see what's going on in section 2.5 next. We're still talking about limits. We're still talking about single-side limits. So limit as you come in from the left, as you come in from the right. But the major thing we're trying to get into is continuity is about direct substitution. So let's see how this all goes finally. Let me clear off this annotate. And here we are. The definition is really, really terse. It just says a function f is continuous at a number a if you take the limit as x goes to a, f of x just turns into f of a. So that's pretty much the whole idea with continuity. If this equation breaks in any reason, and there's several ways it could happen, we'll just say f is not continuous, or we can just simply say f is discontinuous at the number a. So a lot going on all at once with this. Sure, it's a short statement, but the notation is packed. Let's blow this up just a little bit more. So if we're talking about continuity at a number a, first thing we do is put a as the value that the x tends towards in the limit. So a goes there. If this is fully continuous, then we can directly substitute in the value of a in for x. And that's what's happening right in that location. So that is by direct substitution. So I want to draw just a quick graph down below just to give a feel for what does continuity look like and what does a lack of continuity look like. So let's do just actual real numbers so that's more concrete. First one, let's go and have a special value at 2, then 3, 4, 5. So at 2, I'm going to put just a tiny dot here at height 1, just to remind me I want the curve to go through there. Then at 5, let's jump up to 3. I want to have a point at height 3, so let's make that a big solid dot. Then maybe an open dot here at height 2. So that's our curve so far. So drawing it all out, comes in, goes through that point there. That point didn't have to be too big. I just wanted to make sure I hit that location. And let's say it goes through towards the open circle. So here we looks like we have what we called in the prior sections, a removable discontinuity. And then it just carries off. This is what makes it removable. There's one point removed that would have given us a nice continuous curve. So I'll put a little arrowhead here to say it's continuing off in that direction and continuing off in that direction. So there's two interesting spots to look at. There's what's going on here and what's going on here. So let's take a look at the limits then. Any questions about the graph so far? Okay, well, I said take a look at the limits, but if you're talking about continuity, the function value is just as important. So let's actually focus on the f of a as well. On the left here, we'd be looking at f of 2. F of 2 comes out as a value of 1. And over here, we're looking at f of 5. These are always tricky, especially with the limit mixed in. But if we say f of 5, we go through that point and we settle at the solid dot, which was intended to have height exactly 3. So there's f of 5 equals 3 there. And one moment, I think my screen brightness was down. Let me fix that. Okay, I can see the colors better. That helps out. Okay, so continuing on, we looked at what's happening on the right-hand side. Now we want to look here, what's happening in the limit. We want to take the limit on the one in blue as x tends towards 2 of f of x. Well, nothing special happens to this. As you tend towards 2 on either side, left or the right, the height of the curve is getting closer and closer to a height of 1. So this one just turns into a 1. But this one's tricky. Let's do this all over again. We're looking at the left side of the equation for continuity. We're taking the limit as x tends towards a. Our a value here is going to be a 5, so limit as x tends towards 5 of f of x. Anyone see what this limit should equal? Oh, we got a chat, thank you. Looks like almost a tie. There's a couple competing answers, but thanks for the contribution on this one. Some say 3, some say 2. But the idea with the limit is we never actually put in the value of 5. We only do that if we're doing this right here, where it says f of 5 is 3. So in a function value, you'd come up and through and take that height. But the limit is always tricky with these kinds of graphs. What it's saying is you're getting closer and closer to 5, but never actually arriving. We just want to know, what is the height as you get closer and closer to, what is the height actually approaching? On the right-hand side, it seems to be getting closer and closer to the number 2. On the left-hand side, it decreases and settles around height 2 as well. So the limit on this one would be a 2. So now we're ready for our conclusions. Let's use a slightly different color to make this pop out. On the left-hand side, we're able to draw this curve without ever really lifting up our pen. It's just a nice smooth curve going through here. Even if we didn't do the dot first, we could draw the curve just as is. But notice that this actually happened. The limit, as x tends towards 2, of f of x equals f of 2, because they're both equal to 1 exactly. So we got that equality right in the middle to check out, and this then implies f is continuous at x equals 2. No break in the curve, and the equation here worked out just fine. But moving over to the right-hand side here, there is a break in the curve. We're going to call this a removable discontinuity. So let's say it again here. Removable discontinuity. And what goes wrong with the limit? We'll notice in the original equation that defines continuity right up here, we actually have a breakage. There's no equality. We cannot say lim as x tends towards 5 of f of x actually equals f of 5. That's because f of 5 takes the value 3, but the limit as x tends to 5 of f of x, it takes a value of 2. So in the middle, we have not equals. They're different quantities. And this then implies f is discontinuous at x equals 5. And the discontinuity, definitely easier to read off the graph, but working it through the equation, seeing what the original equation up here is trying to convey, that's actually pretty tricky all on its own, I was trying to say. So this is the equation that captures what we're seeing on the graph, making this discontinuous and calling this continuous. Well, any questions, folks, with that first rodeo on that definition? Okay, so in the essence, this is what continuity looks like. Again, you should be able to have your curve drawn without ever making a break. But if something weird happens, if the limit doesn't exist, if there's a removable discontinuity, or worse, we saw other worse issues, that's when we have a discontinuity on the function. So let's change gears here next. Here are the remarks for kind of what we were seeing up here on the graph as well. In order for a function to be actually continuous, you really need several conditions. So continuity on f means the function is defined. If f of a is undefined, then you lose continuity altogether. Next, the limit on the left-hand side has to exist because that's part of the definition. If this limit did not exist, we would never have said it was continuous there. And finally, once we take the limit, we have to have the limit as x approaches a exactly equal to f of a. So that's what was going wrong right here. The function is defined, f of 5 is 3. The limit does exist, the limit equals 2, but they're not equal to each other, and that's what broke continuity. So it's kind of amazing in a certain sense that that's the equation for continuity right there. It's really just very simple to write out, but it's harder to understand, and it really implies all this other information all at the same time. Any questions, folks, with the follow-up remarks there? Okay, well, let's keep on going. Here, to me, this is where it gets a little bit tricky. What's tricky about this is single-side limits on their own is tricky. when we start looking at them in the earlier chapters. Let me make these just a little bit larger so we can focus on them. 16-point font should do the job. So we have a single side limit here where x is approaching a from the right. So x is always above a. We'll say the function is continuous from the right at a if this limit happens to exist and equals f of a. Notice you have to have that symbol, the right-handed limit, for that definition. Continuity from the left at a gives you just about the same equation, except the sign here says you're taking the limit as you approach a from the left. Again, I'd say this is pretty tricky, so let's definitely take some time and draw some graphics out for this. Any questions first, folks, before we take a look at these limits? Okay, so we need another big graph. Here we go. And let's take one interesting limit when we go off by -1, 2, 3, somewhere out here at -4. So at -4, I'm going to draw two portions. I want a solid dot coming in like that, open dot just above it, and let's let the curve do this. It's going to come into that dot in this kind of way, leaves going off in this direction, and let's do another situation over here on the right next. So how about something interesting happening at 2? We'll do a solid dot and an open dot just like before. And let's see, how about we make this one go in that kind of way? And from here, the curve is just going to careen off in that direction. So this is one whole function coming in 3 different pieces, but this is all y equals f of x. Now I want to take a look at several limits on this and just see what's going on both of them. Let me take a screenshot so we can scroll down here if needed. Okay, so first, the limit on the left-hand side, well, I should have also put in some extra marks here. Let's say this is at height 1, this is at height 2, and let's make this be, how about, oh, geez, -1, looks like -1.5 if we're keeping our scale on that. I forgot the y values on that axis, so sorry for the extra little mess there if you're cramming them in like me. But now I want to take a look at the limits in this region right here first. I guess yellow highlighting will work. I thought it was circling something with the pen. There's really 2 interesting limits. You can come in here from the left, or you can come in here from the right. Let me put a 1 there. Let's say we first do lim. As x approaches -4, coming in from the left. For doing that limit, we're coming in on values where x is always less than -4, so we're following this curve up. And this one looks like it would have a limit of f of x equals to -1.5. Any questions, folks, with that first limit there? Pretty much a review on single-side limits. Okay, let's take another look on above. We can take the limit if we're on this portion of the curve as x approaches 4, but this time we're only coming in from the right-hand side. So we put that plus symbol there to convey it. Let me just move that down for the moment. So it's a limit as x tends to 4 from the right of f of x equals, and this one, as we come down, I was trying to convey it's going to have a height of 1. Last thing to take a look at is the function value, f of -4 itself. This one looks like it comes out as a -1.5. Okay, so that's all the limits we have going on the left-hand side. And let's do the same thing on the right-hand side. So first we'll take the limit as x approaches this positive number 2 coming in from the left. So that writes in as lim x approaches 2 coming from the left of f of x. Oh, and before we do that, we got a chat. Oh, -4 from the right. Oh yeah, it looks like you forgot my negative sign. Thanks for spotting that. So I need a negative right in the middle there. I think we can just do some really quick surgery on that. X approaches -4. Thanks for spotting that, Jamie. That was going to be invisible to me until you said that.
I
Other
have a
questions or corrections?
question really fast.
Sure, go ahead.
Um, so as x approaches -4 from the right side, the limit, it wouldn't be -1, it'd be 1 because that's the highest point of the curve.
Oh, that was a second mistake. I put 1 here, but that was meant to be -1. I'm really glad you pointed that out as
Okay,
well.
gotcha. Okay.
So
I
negative
was
1
worried that I
here
was feeling.
and here. I think I'm just not drinking enough coffee this morning. Let me circle my omissions. There should have been a negative sign there, a negative sign there, and on my graph, a negative sign as well. I think we needed to pause right there just to make sure everything is, once you find one mistake, it feels like others propagate. Does that look better to folks so far? Okay, awesome. And thanks for stopping the lecture right at that point. If the numbers look weird, if the math isn't mathing, always a great time to ask a question. I appreciate it. Let me get off those temporary symbols just so that they're not too busy when we're looking at it. And now just double checking, I'm approaching 2, coming in from the left. So yeah, that looks good so far. This is meant to have a height of 1 when I threw in that tick mark. And now let's go to this height, or this part of the curve. That means we're taking the limit as x approaches 2, coming in from the right of f of x. This one, as we come in from the right, looks like its limit should be 2 exactly. Then last thing to calculate is just f of 2. On this graph, f of 2 takes on the value of exactly 2. And now, well, we still haven't resolved if we have continuity from the left or at the right at any one of these values, but we're about to. What we needed were the equations. So let's focus on this one first, and then we'll do this area next. So here's those equations down below, just as a quick reference. So it says on definition 2, you're continuous from the right at the number a if, as you approach a from the right, the limit of f of x equals f of a. So let's take a look. On this one, we have a function value equal to -1.5. It latches up with this one, -1.5, but its one is coming in from the left. So we have a matchup here to here. So it says f is continuous from the left at a if you take the limit as x tends to that a, -4 in our problem, from the left, and you get the function value. But it looks like these match up. We can now say, therefore, the limit as x approaches -4 from the left of f of x equals f of -4 due to the portions highlighted in green here. And that tells us finally, let's say, and so f is continuous. I'll abbreviate continuous quite often as just CONT dot for continuity. Decent shorthand since we write that out a lot. So f is continuous at x equals -4. Oh, that's not going to work. Let me go down just a touch. From the left. Any questions, folks, with that conclusion here?
I have a question.
Yeah, go ahead.
So is it just a coincidence or does it have something to do with, I don't know the correct term, like the black dots rather than the circles?
Good eye, Jamie. It has everything to do with those black dots. And that's going to be kind of a really quick shortcut to analyze this once we see how it goes here. Continuity from the left meant, as you came in from the left, you had to land on that solid dot. So that's a really great way to see it on the graph. Let's put in that shorthand there. Any other questions about that first? Okay, I'm glad that you observed that. Same kind of thing is going to happen on this one. Observe as you come in from the right, you land on a solid dot. It's that alone that gives you continuity from the right. To see how it works with the definitions, that's the hard thing for sure. And that's why we're writing out these separate limits. But if we're just analyzing the graph, this is the way I encourage you to think about it. let's put here just a star. Continuity, C-O-N-T for continuity, from the left requires, that's a very strong word in mathematics when you say requires, this dot solid. And while we're up here looking at it, let's say the same statement up here, continuity from the right. Let's use that important word, requires this dot is solid. I think I forgot a verb over here, but we'll go with that. So that dot there is what was required to get continuity from the right. Other questions about that way of visualizing it? Okay, now let's see if we can do the harder thing. Here's the definition. Let me make it slightly bigger. We have three different limits here, or excuse me, three different expressions, two of which are limits. Let's see if we really have continuity from the right. So continuity from the right says, as you take a limit, as x approaches 2 from the right, you get exactly the function value. So that was this limit here. Here's the function value. And now we can say, once I get the pen going, there we go. Therefore, little triangles are just a quick way to say in conclusion or therefore. The limit as x approaches 2 from the right of f of x equals f of 2. And so f is continuous from the right at x equals 2. So those are the two definitions down here in action. Also right up here from where we're copying them above. But as was remarked earlier, continuity from the left or the right, you can also just read it off the graph by seeing where the solid dots land. If both of those were open circles, we'd have neither continuity from the left nor the right. Same here if those were both open circles. Well, any last questions, folks, on single-sided continuity? Okay, I don't know why I said last questions. There's no last questions. If we have to come back to this right here, just go ahead and ask. No big deal. But for the moment, unless there's other questions, let's take a look at how this comes together with some actual practice problems. These all just been definitions. So we looked at double-sided continuity. That's what it would look like. The curve doesn't have anything funky going on with it whatsoever. No open circles. It's just a nice smooth curve that's connected. This is what discontinuity looks like from a single side, or excuse me, from double-sided. And these are what the single-sided continuities look like. There's a solid dot somewhere, but then the curve jumps down, and we have open dots and such. So now here's what some of the questions it could look like in the homework set. You'll occasionally just be given a random graph of a function and asked to assess what the discontinuities are. So looking at this is all one function, y equals f of x. It comes with several problems that we can see here. For example, there's a domain value missing here, implied by the graph. This one has a domain value, but it's way down here. The point on the function isn't with the rest of the curve. That looks concerning. But as far as continuity goes, no problem there. We have nice, smooth, continuous curve. Well, it's not smooth. It looks sharp there. So we'll say something about that location in chapter 3. But then there's another issue at 4, another issue at 5. Really, what the way we're treating example 1 is, we're looking at a catalog of the very most common ways in our class where we're going to find discontinuities. So here's the one function. We're going to state the numbers where the graph is discontinuous, and also the type of discontinuity. So that's the major takeaway in this section. We're once and for all formally defining these types. So starting right here at 1, there's definitely a problem right here we can see visually, since there's a hole in the graph right there. So at x equals 1, that's where the graph of f is discontinuous. The type of discontinuity is called removable. Removable discontinuities are a bit special when it comes to limits. It means that you can fix this by defining one point. If I define a point there, we've removed the discontinuity. The whole issue with the discontinuity is it's just a problem right at 1. F of 1 is undefined, in other words. Well, that's the issue there. And at 2, that's another discontinuity. The function is defined, f at 2 equals 1. However, at x equals 2, it's still a discontinuity, and we still call this one removable. This one's removable in the sense that you could fix the problem by taking this point, redefining it so it's up there, and just plugging the hole. So it's a really fast correction here, just moving one point up. Discontinuity is gone. So whenever we say something is a removable discontinuity, it means there's just one point that has to be fixed to correct that discontinuity. Any questions, folks, with the first two problems at x is 1, x is 2? Okay, anyone volunteers for the next discontinuity? Yeah, good call. At x is 4, this one's called a jump discontinuity. We've seen these before, but again, we're finally formally defining each one of these. And what makes it a jump is, for following the curve, sure, there's a sharp point here and you suddenly change directions. If that was a roller coaster ride, that would be probably something that would get the park shut down. But if you continue on in this way, everything is fine. But the curve jumps down to a new height as you proceed through 4. So that's a pretty major discontinuity. It's not removable because the fix to this would require this whole piece of the curve to move up. But that's every point on that entire curve has to change. So that's a more serious discontinuity, and we'll say at x equals 4, this is called a jump discontinuity. So last one, definitely a problem at x equals 5. The way this is being conveyed is you can't draw this curve without ever picking up your pen, because this part of the curve just goes up forever off the page, never actually crossing the dashed line. Same issue with the other side of the curve. It's also going up forever. So anyone recall what we might call something like this as a discontinuity?
An asymptote?
That's a great way to say it. An asymptote says that there is an infinite discontinuity here. If you said x equals 5, the discontinuity is due to an asymptote, that would be perfectly correct. I would think that's a great answer for that. Usually what the book would say is they'd abbreviate it to infinite discontinuity. That's just the book's official way to express it. So again, if you said vertical asymptote, so there's a discontinuity, that's just great as well. At x equals 3, no discontinuity there. It's just a sharp point, which is a bit of a concern. So we have to come back to that shape that we see there in chapter 3. What we'll say later is the function is not differentiable there, but we have to say what in the world that even means. As far as continuity is concerned, though, perfectly normal point. Other questions at the moment?
Would you mind explaining again real quick how you would fix the removable discontinuity at 1 and 2?
Yeah, absolutely. So if we change this function, we're not any longer going to get y equals f of x. It'd be a brand new function, y equals g of x. And if we decide we want a new function without those two discontinuities, we have to define a new point right here. So now continuity goes through this location. And then over here, we have to redefine the point. So that would be deleted. we would say that f of 2, well, now it's g of x, we would say g of 2 has to be 2. So that's the way we would fix the two discontinuities if we wanted a continuous graph here where there was removable ones.
Gotcha, thank you.
Absolutely. Other questions at the moment? Okay, so those are our different kinds of discontinuities. And just by the way, just for a review topic, another reason this one's called an infinite discontinuity is that it's a reminder that if you took the limit as x tends towards 5 of f of x on this graph, you would get positive infinity due to that vertical asymptote. And so that's why it's called an infinite discontinuity. So 4 discontinuities on this one, and a follow-up question says, for each discontinuity stated in part A, determine whether f is continuous from the right or from the left or neither. So let's take a look. At x equals 1, remember that comment we made before, there's got to be a solid dot somewhere. Here it's completely missing, so this one has neither. Meaning it's neither continuous coming in from the left nor the right whatsoever. This one did have a solid dot, but let's scroll up just for a moment to get a feel for what's going on here at x equals 2. For that to be continuous from either the left or the right, it's got to be more like this. The curve has to approach and end right on that solid dot to get continuity from the left, or vice versa. The curve has to come in and land right on the solid dot for continuity on the right. But if your solid dot is totally isolated, say like over here, that's another neither. It's neither continuous from the left nor the right on that point here. So x equals 2, neither. I'd say the more exciting one is over here, x equals 4. We need to know on this part B, is this continuous from the left or to the right? Anyone see the direction? Yes, absolutely. It's continuous coming in from the left. So as we come in, another way to see it is, if we come in from the left, we land on a solid dot. So that is continuity from the left. Once you see this problem and the definition just right above on these notes, you'll notice a pattern here. If you say continuous from the left or continuous from the right, it's always relative to a jump discontinuity where one end or the other end is solid. Continuous from the left or right never work on removable discontinuities, and they also never work on a vertical asymptote. We can force it to work, but you'd have to do something like this. Define a new point, let it come down and out like that, and just let the other end move upward like this. But on this graph, if both ends are moving upwards towards positive infinity due to the infinite discontinuity, at x equals 5, it would be just another neither. So for single-sided continuity, it was just this one right here. Any questions at all, folks, with the definition or the exercise here? I would say they are mutually exclusive, but it depends on how you mean. Yeah, I think I'm agreeing with you. If you say, for example, continuous like this, you're talking about single-sided continuity. Here, we would say that this is discontinuous using the old definition, but it is continuous from the right. So no, I agree with you, Kiana. They are not mutually exclusive because of this extra definition here. Continuity from the left and the right makes it a little bit extra tricky. Does that help out there with that question? Yep, absolutely. Any other questions so far? Okay, so Again, this is a lot of work where it feels like we're mostly just analyzing graphs and working through it. We did a whole lot in that in chapter 2, and that's partially why the exam was heavily represented with graph works as well. But in the end of the day, we're talking a lot about continuity. I should give you a preview of what this is heading towards. Continuity is amazing if you're trying to take a limit of a function like this, and you happen to know it's a continuous function. Limits of continuous functions are just a direct substitution property. So that's what we're trying to get back into. But before that, we have a couple more things we want to take a look at. And I forgot about our example too, so let's definitely finish this one off. I wrote here for example 2 that this is sometimes a question that could be asked on a real exam. It says, write an equation that expresses the fact that the function f is continuous at the number 5. The reason this is a potential exam question is more because there's 3 major topics in calculus. There's continuity we're looking at right now, then it's differentiability, we'll see in chapter 3, and integrability, integrals that we'll see in the later chapters starting in 5. But every one of those concepts, they all come out through some kind of limit. And so these kind of questions are just a reminder of how things are defined. So if we say something is continuous, that means we're taking the limit as x approaches some number. They have to specify the value, so here it's saying x must approach 5. The limit will be for the function f of x. And continuity means we get to do the following. It's going to be dead on equal to the function sorry for the scribbling, let me fix that. It's going to be equal to the function where we directly substitute in the value 5. So that's a potential exam question, potentially on exam 2 and the final exam. Really pretty fast, it's just a reminder, what did we mean way up here when we originally defined continuity? Essentially, we're just saying take x, that's a, plug it inside f. Sorry for the rapid scrolling there. Any questions, folks, with that example 2? Okay. Again, we kept mentioning when you think continuity, you're really just dealing with a direct substitution property. And here's where it happens. Visually, this is direct substitution. Well, with that out of the way, here's the probably harder question in the notes, example 3. We've seen these kind of questions before, but now this one is only about continuity, it turns out. We're trying to sketch the graph of a function that satisfies every one of these different properties. So that looks like there's 6 so far. This one's kind of a technical property. This one means we can't have any part of the function undefined. So if there's a hole somewhere, we need to put a solid dot above it. And there can't be a region where there's just no curve whatsoever. So we want defined this way on all real numbers. Let's start off by just putting a really long x-axis. Kind of compressed vertical axis. That's just due to the limitation of the space here. We'll come back to this one. The function is defined on R. Make sure we really made that happen. And here's where it gets a little bit interesting. This is like what we were just taking a look at, but we're doing this graph backwards. It says here, the function is continuous only from the left at x equals -1. So we'll go to -1. Continuity from a single side just means we're going to put 2 open circles for sure. One of them and only one of them has to be made solid. So let me make one part come in from the left, one part come in from the right. And for this statement right here, which dot would you make solid? The top one or the bottom one? Any volunteers for which one?
The bottom.
Good call, Alejandra. The bottom one has to be solid because continuous from the left means you come in from the left and you land at a solid dot right there. So good catch on that. Notice I only drew a little bit of the curve coming out to the left, a little bit of the curve coming out to the right. Because there is something like 4 other conditions, we don't want to draw it too far and have the other conditions suddenly contradict it. So let's move on to the next one. It says here, there's a jump discontinuity at -3. So let's move over -1, -2, -3. And I mean, here at -1, that is a jump discontinuity. They're asking for another one, but they didn't have any special instructions. So continuous from the left, right, or neither is just fine on this one. Let's make it continuous from neither side, just to show what that would look like. So here it comes in towards an open circle. Let me make that look a little bit nicer. As we move further to the left now, let's put another open circle going this way. I think we can now let it go just cleanly off to the left, since every value afterwards is positive. Now, if we leave it like this, I probably wouldn't take off a point, but we actually did break condition 1 in a really minor way. The function would not be defined on all of R because it's undefined at -3. So the fix is just an extra solid dot. Again, that's a pretty small technical issue, but if you missed that, I don't think I would take off a point there, but this is what we're going for. So now here, it was continuous from the left to the solid dot, but over here, it's neither continuous from the left nor the right because you have to land on solid dots for those single-sided continuities. But all we were asked to do at -3 is make a jump discontinuity. So we went from here, we jumped down to a function value, we jumped down again to the rest of the curve, and that's what we needed, a good jump. Any questions so far, folks, with those conditions? Okay, looks like we're going to removable at 2. So let's go 1, 2. A removable discontinuity just means there's going to be an open circle somewhere. Let's make it way up here, just because we can put that anywhere you like, just to be creative. Let's make it be up there. So this right portion of the curve has to come up inside here. And to make it removable, we need another dot down below, and the curve carries out. So a removable discontinuity can never be a jump discontinuity on this one. It's as if you're drawing a normal curve, but then you're just grabbing a point, moving it off the curve, one single point. So now we've got removable there. Any questions, comments, or concerns so far? Oh, that's a good question, Dana. So if we took off that solid dot right here, oh, my Microsoft Word gets a little bit laggy sometimes. There we go. If we took off the solid dot just like that, it would still be removable. And so this would be a great solution so far. The only thing that would conflict is the original information. The function needs to be defined on R. What we mean by R is all real numbers, or you could prefer, if you prefer, you could write this as the interval from -infinity to +infinity. And so that's the only thing that went wrong. We're missing the function being defined at 2, so we could put a solid dot somewhere, and now it's defined. But I would say the major reason this first bullet is here is just so that we don't have something that goes like this. Your functions should really be connected. There shouldn't be, say, like a void space in the middle. So that's where you could potentially lose a point on this. Not if there's one dot causing a problem necessarily. I would probably just draw it in and mention it. So to make it define on all real numbers, we really want that part, connecting the dots where we can, essentially. Other questions at the moment? Okay, so we did it, folks. At x = 2, we make it a removable discontinuity. Next one it's asking for is an infinite discontinuity. So let's go 2, 3, 4, 5. An infinite discontinuity, like was mentioned earlier, you could just think of that as a vertical asymptote. That's a complete synonymous situation. And that's a great thought because we're in fact putting in a vertical asymptote. So an infinite discontinuity at 5 could look like this. It's just heading towards the vertical asymptote. The limit would be negative infinity. And notice I only drew one side this time. That's allowed. As long as one end is going off to negative infinity, you have an infinite discontinuity. So it doesn't have to be, say, like this one, where both ends are going upwards. It could be one end. Ends could go in different directions, one up, one down. And on my graph, I'll just have one end going down to negative infinity. Still produces the infinite discontinuity. And the reason I only want one end going down is because of this. Something changes as we go to the right at 5. We want continuity from the right. What does that mean? It means the curve has to be coming in from the right. So here it is. But we have to be very careful because that's a vertical asymptote. You can never cross it, but you can touch it. It could do something like this, for an example. So continuity from the right means we landed on a solid dot as we came in from the right on the vertical asymptote. It still satisfies the vertical line test because as this curve comes down, this portion never actually touches the vertical asymptote whatsoever. This is concerning, but it didn't cross the vertical asymptote, and so we still are okay. We have a real honest function. It comes in several weird pieces. Lots of weird things happen to this function. But altogether, this is one function, y equals f of x. We did problems like this before for quizzes, one on the exam, but I'd say we probably won't see too many more of these on future upcoming exams. They are pretty tough and tedious to write out, but still it's good practice to see at least one more time in the notes. Any questions at all, folks, with those concepts of continuity? Okay, so all the way through example 3 is the more conceptual work on dealing with continuity. Going beyond, we have a big roundup of theorems, a whole bunch of theorems altogether here, and example 4 that goes right below. The purpose of this is, example 4 here is just to get a feel for what all these theorems are saying. Then we're going to apply them down here for taking limits as fast as possible, essentially. But first we need to say, what are the things that we can call continuous? If we know something's continuous, for example, we can do a limit really, really fast. In fact, let's take a really small trip down Memory Lane just to see where all this is really going towards. So pause right here. Let's go to the Moodle course. In section 2.4, we're doing limits just like we're doing in this section. And let me find one where we had some extra tools to help us out. There it is. If we know we have a polynomial function or a rational function, taking the limit just boiled down to this right here. If you look at that really carefully, let me pull this out. The limit as x tends to a of f of x equals f of a. Well, that right there, sorry, let me get my windows adjusted here. Forget this is a little challenging some days. There we go. That one's controlled now. Let's go back to the notes. Now here's our original definition for continuity, and notice the parallelism. And the direct substitution property that we said works for polynomials and rational functions, it says the limit as x tends towards a of f of x is f of a. That's the same exact statement right up here. So what we're doing in section 2.5 is we're trying to go beyond the polynomials, beyond the rational functions, and collect a whole category of functions that are continuous. So it starts right down here. So theorem 6 gives us a whole category of continuous functions. Let's go in order, otherwise it would just be weird. So it says here in theorem 4, if you know you have continuous functions, f and g are known to be continuous, say they're polynomials or rational functions, and c is a constant, then every one of these functions is continuous. So you can add a continuous function to another continuous function. The result is still continuous. Likewise, subtracting continuous functions, multiplying a continuous function by a number, or multiplying or dividing, as long as you're not dividing by the zero function, all of those would be continuous functions, just knowing the components are continuous. That leads us into theorem 6. Which functions are continuous? Let's read this one carefully. The following types of functions are continuous at every number in their domains. That's the polynomials. And when we say polynomials, that's what we're referring to back over here again. If we take the limit of a polynomial, I'm not sure why I scrolled down there, but if we have a polynomial function, it has the direct substitution property. So polynomials are great. Let's put down just a quick example. I thought I had one on those notes there. Something like this would qualify. F of x equals x squared minus 3, for example, for a quick polynomial. For power and root functions, these would be functions that might go y equals x to the 3 halves, for example, or y equals 5th root of x. So all those functions there are also considered fully continuous. So you can use direct substitution properties on them. Going even further, exponential functions, that's referring to things like y equals e to the x, like we saw in the section 2.2 notes. Or for another example, maybe y equals 10 to the power of x would be exponential. Rational functions go along with the polynomial ones. And that could be something, say, like f of x equals x plus 4. X squared minus 8 would be rational. Trigonometric functions are all continuous, but our course doesn't assume knowledge on trigonometry. It wasn't a prerequisite. So let's skip over to the logarithmic ones. I think that's fair. Every logarithmic function is continuous on its domain. And those would be functions that go like this. F of x equals natural log x, for example, or maybe y equals log base 7 of x would be the logarithmic ones. So all these are terrific functions. And if you take any one of these functions, combine them by adding, subtracting, multiplying a scalar, multiplying them outright or dividing, your results are still continuous. Any questions, folks, with theorem 6? Okay, theorem 7 is a technical tool that I posted here just for the sake of completeness. It's weird to skip a theorem, but we won't have cause to use this theorem 7 in the notes currently. When we do go to use this thing, I'll cite back this section to show where we got it and how we're going to use it. But theorem 8 we will use, and this one's pretty special. This is a lot of different ways to combine functions, but there's one really interesting way to combine functions, and that's through the function composition. We indicate a composition by saying f of g at x, and it's just f composed with g of x. So your g of x function is the input. So if g is a continuous function at a, if f is continuous at g of a, then the essential point of this is the composition of functions is also continuous. So we will use theorem 8 right here on these notes. And that is a lot of technical theorems out of nowhere about continuity. The thought here for pulling this up is it's really just extending what we were saying here, direct substitution. We were working our way to continuity all along. But to get a feel for how those theorems go, let's work out example 4. Example 4 is one of those examples where I wouldn't ask this one on a quiz problem or an exam problem. Its whole purpose is just for these notes to understand what's going on with the first theorems up above. So let's go through this carefully. Part A wants a domain. Then we'll explain using the theorems above why it's continuous on its domain. Looking at the function, it's not the friendliest thing out there. It's got a root of a natural log in the numerator, x squared minus 9x plus 20 in the denominator. But the denominator is a little bit more friendly. Maybe the first thing we should do is factor that thing. So let me just go to the right, maybe. This is equal to the square root natural log x divided by factorization of that would be x minus 4 times x minus 5. Foiling this would produce the original polynomial. Now to get the domain, we're just going to work in stages. Let's get the domain of the numerator. Might as well start color coding them as well. And then we'll get the domain by considering what's going on in the denominator. So first, for a bit of a review, the square root function is nice. Its domain goes from 0 to infinity, but it's being restricted by the natural log function. Let's put down a quick graph on that. The natural logarithm function looks like this. It intersects right at 1, but it has an infinite discontinuity. After we cross through at 1, it starts increasing, but very, very slowly. But that's already a problem here. This tells us that the domain for natural log x, let's write natural log x, has domain 0 to infinity. All those numbers from 0 to infinity are because of this graph right here. You can't actually put in 0 inside your natural log. You'll get a domain error. If your calculator is really expensive, it might give you a complex answer, but we're sticking to real numbers, so we're not doing the complex values. So the square root function does take this 0 to infinity. So now we can say, and so root natural log x has domain 0 to infinity as well. I think I'm going to need more space, but we're nearly done with that. Any questions at all, folks, with the analysis in the numerator? Okay, the major thing we were trying to watch out for with that square root was if for any reason, if for any reason we got negative values, then we would have to adjust our domain here, and I think we do see a reason. Let me strike this through. This is a mistake right here, but that's a mistake I want to leave on the notes just in case you come back to it and say, oh, that's an easy mistake to make. At least it was for me. The problem with this function is this is the natural log function. It's going inside a square root, but we're trying to avoid taking square roots of negative numbers like that. We want only real number outputs, and that's not a real number. So our trouble then is right here. This is right at 1. And right at 1, we get a value of 0 from the natural log. But if you go to the left, you're at negative infinity. So sure, natural log x has domain 0 to infinity. And so if you take the square root of natural log x, you really have to start right here to get positive results. Let's put in the correction by saying, however, natural log x is bigger than or equal to 0 for x bigger than or equal to 1. So the root of the natural logarithm of x has domain 1 to infinity. The bracket right here at 1 is conveying you can put 1 inside here. Natural log 1 is 0, square root of 0 is 0, and nothing goes wrong. But 1 is the minimum number that you could actually put in. Otherwise, you're going to put in negative values inside the square root. So that numerator came out a little bit more involved than we wanted. But the denominator is not so bad. There are certain values you can't put inside h of x. For example, you can't put a positive 4 or a positive 5 inside there because those would be 2 divisions by 0. So we can say x cannot be 4, x cannot be 5. And here's our full conclusion finally. Again, this problem is a little bit nastier than normal. This is not a quiz problem, nor a homework problem, nor an exam problem. We're just trying to get a feel for what's going on up here. So sorry for the weird domain issue there, a little bit more complicated than it was needed to be. But coming back, we can say, therefore, h has domain. We start over here at 1. That's the smallest number you can put inside there. But it doesn't fully go off to infinity because you run into a problem point here. You cannot put in a 4. So we go brackets to say 1 is in the domain. A 4 parenthesis says the 4 is excluded. Then union is just saying add another set. Start at 4, go up to the next problem point, 5. Then keep on going. Beyond 5, there's no other issues. So from 5 to infinity, we have our full domain of that original function. Again, a little bit more involved than I wanted on that one. Sorry about that. But any questions at the moment? Okay, so now we're going to use theorems 4, 6, 8 to explain why the function is continuous at every number in its domain. Let's start off and again work in pieces. we need to explain why that thing's continuous, the root of the natural log x. Well, that one is going to be, because the natural log x is continuous function, root functions are continuous, whether it's a fifth root or a square root. And theorem 8 says, well, that's a composition. The g function is the natural log. The f function is the outer function, the square root. And so we can now convey this by saying, since natural log x is continuous and root x is continuous, by theorem 6, that's one that had all the categories of the different functions. Theorem 8 says the root of the natural log x is also continuous. Then the denominator is not so bad. That's a polynomial function of degree 2. Let's scroll up for just a bit. It says here, polynomial functions are also continuous right out. So let's go now say next. X minus 4, x minus 5 is also continuous. That deserves an exclamation mark because we're nearly through this problem, folks. So what do we have? We have a function in the numerator that's continuous, function in the denominator that's continuous. Now we just go use theorem 4. Theorem 4 says you can do all sorts of algebraic manipulations. And this is essentially what we're looking at. A continuous function divided by another continuous function. We excluded all the values where it's going to come out as 0 when we restricted the domain by taking out 4 and 5. So now we can say, therefore, h of x is continuous since the numerator and denominator are both continuous. So that's wonderful. Continuity is a really important property, and we have lots of ways to show different kinds of functions like this one, kind of a worst case scenario, is in fact a real continuous function. Well, any questions at all, folks, with running through the analysis on this one? Okay, looks like we have just a little bit more time, but with all this work we've done on continuity, here's how it finally comes together. Example 5 says, evaluate the given limits. These are going to be limits you'll see again on exam 2, but the hint is they're not so bad. We have a square root function, which is continuous. On the inside is a rational function. That's continuous as well, because when you plug in x is 0, you're not dividing by 0. So here we can say, by continuity, this is going to be equal to, let me just put an arrow to say, this is what we've done. Continuity is a direct substitution, so 0 gets placed inside everywhere x occurs. This is now the root of 0 squared minus 4 divided by 2 times 0 minus 9. And that's fantastic. That means all the hard work we've dealt with limits is basically been eliminated. The work becomes root of -4 divided by -9. Thankfully, that turns into a positive number, so it's root of 4/9. The root of 4 gives us a 2. Square root of 9 gives us a 3. And so that one is completely done. Best limit ever is if you can use continuity. In section 2.4, we tried to use continuity, but we continually ran into cases where we could not use direct substitution, so we had to algebraically maneuver the function, change it, cancel it, simplify it. But for these problems, these are continuous functions, and so all you can do is direct substitution. Let me make this one, next one, a little bit bigger. Any questions with our first example, 5 part A? Okay, well, let's do it again. This is an exponential function, which is continuous. Then we have a root function, which is also continuous. A polynomial on the inside is continuous. So we get to say again, by continuity, and you don't have to say this statement when you're working out a problem, say on an exam or a quiz, but this is more for the sake of notes to explain how we're getting to the next step. So by continuity, we use direct substitution. Let's try to convey this a little bit more accurately. Direct substitution means we're taking 2 to the power of square root of 2 squared plus 1. So this will be the square root of 4 plus 1, 2 to the power of square root of 5. Nothing more to do with that. That is in its most simplified format. So the problem ends right at this stage. Any questions at all, folks, with part B? Okay, doesn't seem like it directly, but pretty much the way we did part A, part B, is we took for granted all of these theorems are saying we have continuity whenever we're looking at those kinds of different functions. This was more of a deep dive on exactly how you would have to say that. It takes a lot of actual writing, but this is what the work looks like in practice for typical problems. Oh, sorry, Dana, is that not a 0? That was a 0. Gee, that was supposed to be a 0 there. Thanks for spotting that, Dana and Emily. Direct substitution means you really direct substitute in the actual value. Let me fix that and that. So if it's 0 here, and I even highlight it, that was meant to help me. I should be putting 0 right inside there. Let's correct that limit. So now it's 2 to the power of root 0 plus 1 means it's 2 to the power of root 1. Square root of 1 is still a 1. And 2 to the power of 1 is still a 2. My answers are totally different now. Thanks again for spotting that correction there. Other questions or comments so far? Okay, let's see what we have. I think it's one last one to get through. This is a limit as x tends towards 4 on this last one. Putting a 4 in the denominator is not going to give us a 0, so we don't have to do anything like we did in the prior section, say factoring or things like that. Instead, this one becomes, I'm going to be real careful with that 4 this time. Let me highlight it. I think that'll help me. This is going to be equal to first 4 squared minus 4 again. The parentheses here just to convey that's where we did a substitution, a direct substitution. 10 divided by 5 times 4 again. Then minus 1. So that's pretty much it. We just need to simplify this down. Looks like it's 16 minus 4 plus 10 divided by 20 minus 1. So numerator looks like it's going to be a 22 altogether. Denominator is 19. Doesn't even reduce. You've got to like the prime numbers there. So that limit is done, again, as fast as possible. If you compare what we did in section 2.4, we really were kind of doing similar things, but there was some differences. For example, see if we can get just a quick example to see. The trouble with this one is the reason direct substitution didn't work is because it would have involved a division by 0. So we have to factor first. But then at that step, we're using continuity once again. X plus 1 is continuous. And so we directly substituted 1 into that step. The only difference between section 2.4 is that these problems are all continuous, so they didn't need that extra algebraic step. They all went a lot faster. Well, any last questions whatsoever, folks, with continuity? Okay, I'm noticing that we're not done with this section. We got through the main stuff, though. At this point, I'd say you would be able to get pretty far in the homework, potentially complete it just fine if you wanted to. But I want to come back to the notes just so that we can give enough time to look at the application in this section. So Wednesday's class will be kind of fun. We'll finish off one last application, and we'll finally turn all this limit stuff around and define what we mean by the derivative and how to calculate it through a limit. Well, that's all I have for folks today. Any last questions before we call it a day? Okay. And just a reminder, since we've had exams going on and I had an office hour interruption, I'm going back to the ordinary office hours routine on this week. So I'll be back on here at from 3:30 to 4:30 if you have further questions. Otherwise, have a great day, folks, and I'll see you all on Wednesday. Take care.